Monte Carlo methods are a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. Typically one runs simulations many times over in order to obtain the distribution of an unknown probabilistic entity. The name comes from the resemblance of the technique to the act of playing and recording results in a real gambling casino. They are often used in physical and mathematical problems and are most useful when it is difficult or impossible to obtain a closed-form expression, or infeasible to apply a deterministic algorithm. Monte Carlo methods are mainly used in three distinct problem classes: optimization, numerical integration and generation of draws from a probability distribution. In physics-related problems, Monte Carlo methods are quite useful for simulating systems with many coupled degrees of freedom, such as fluids, disordered materials, strongly coupled solids, and cellular structures. Other examples include modeling phenomena with significant uncertainty in inputs, such as the calculation of risk in business. And, in math, evaluation of multidimensional definite integrals with complicated boundary conditions. In application to space and oil exploration problems, Monte Carlo Euro-based predictions of failure, cost overruns and schedule overruns are routinely better than human intuition or alternative soft methods. The modern version of the Monte Carlo method was invented in the late 1940s by Stanislaw Ulam, while he was working on nuclear weapons projects at the Los Alamos National Laboratory. It was named by Nicholas Metropolis, after the Monte Carlo casino, where Ulam's uncle often gambled. Immediately after Ulam's breakthrough, John von Neumann understood its importance and programmed the ENIAC computer to carry out Monte Carlo calculations. Introduction. Monte Carlo methods vary, but tend to follow a particular pattern: define a domain of possible inputs. Generate inputs randomly from a probability distribution over the domain. Perform a deterministic computation on the inputs. Aggregate the results. For example, consider a circle inscribed in a unit square. Given that the circle and the square have a ratio of areas that is I/4, the value of I can be approximated using a Monte Carlo method. Draw a square on the ground, then inscribe a circle within it. Uniformly scatter some objects of uniform size over the square. Count the number of objects inside the circle and the total number of objects. The ratio of the two counts is an estimate of the ratio of the two areas, which is I/4. Multiply the result by 4 to estimate I. In this procedure the domain of inputs is the square that circumscribes our circle. We generate random inputs by scattering grains over the square, then perform a computation on each input. Finally, we aggregate the results to obtain our final result, the approximation of I. If the grains are not uniformly distributed, then our approximation will be poor. Secondly, there should be a large number of inputs. The approximation is generally poor if only a few grains are randomly dropped into the whole square. On average, the approximation improves as more grains are dropped. History. Before the Monte Carlo method was developed, simulations tested a previously understood deterministic problem and statistical sampling was used to estimate uncertainties in the simulations. Monte Carlo simulations invert this approach, solving deterministic problems using a probabilistic analog. An early variant of the Monte Carlo method can be seen in the Puffins needle experiment, in which I can be estimated by dropping needles on a floor made of parallel and equidistant strips. In the 1930s, Enrico Fermi first experimented with the Monte Carlo method while studying neutron diffusion, but did not publish anything on it. In 1946, physicists at Los Alamos Scientific Laboratory were investigating radiation shielding and the distance that neutrons would likely travel through various materials. Despite having most of the necessary data, such as the average distance a neutron would travel in a substance before it collided with an atomic nucleus, and how much energy the neutron was likely to give off following a collision, the Los Alamos physicists were unable to solve the problem using conventional, deterministic mathematical methods. Stanislaw Ulam had the idea of using random experiments. He recounts his inspiration as follows. The first thoughts and attempts I made to practice, The Monte Carlo method was suggested by a question which occurred to me in 1946 as I was convalescing from an illness and playing solitaires. The question was, what are the chances that a Canfield solitaire laid out with 52 cards will come out successfully? After spending a lot of time trying to estimate them by pure combinatorial calculations, I wondered whether a more practical method than abstract thinking might not be to lay it out, say 100 times, and simply observe and count the number of successful plays. This was already possible to envisage with the beginning of the new era of fast computers, and I immediately thought of problems of neutron diffusion and other questions of mathematical physics, and more generally how to change processes described by certain differential equations into an equivalent form interpretable as a succession of random operations. Later, in 1946, I described the idea to John von Neumann, and we began to plan actual calculations. Stanislaw Ulam. Being secret, the work of von Neumann and Ulam required a code name. Von Neumann chose the name Montecarlo. The name refers to the Monte Carlo casino in Monaco where Ulam's uncle would borrow money to gamble. Using lists of truly random numbers was extremely slow, but von Neumann developed a way to calculate pseudo-random numbers, using the middle square method. Though this method has been criticized as crude, von Neumann was aware of this. He justified it as being faster than any other method at his disposal, and also noted that when it went awry it did so obviously, unlike methods that could be subtly incorrect. Monte Carlo methods were central to the simulations required for the Manhattan Project, though severely limited by the computational tools at the time. In the 1950s they were used at Los Alamos for early work relating to the development of the hydrogen bomb, and became popularized in the fields of physics, physical chemistry, and operations research. The RAND Corporation and the U.S. Air Force were two of the major organizations responsible for funding and disseminating information on Monte Carlo methods during this time, and they began to find a wide application in many different fields. Uses of Monte Carlo methods require large amounts of random numbers, and it was their use that spurred the development of pseudo-random number generators, which were far quicker to use than the tables of random numbers that had been previously used for statistical sampling. Definitions: there is no consensus on how Monte Carlo should be defined. For example, Ripley defines most probabilistic modeling as stochastic simulation, with Monte Carlo being reserved for Monte Carlo integration and Monte Carlo statistical tests. Sawilewski distinguishes between a simulation, a Monte Carlo method, and a Monte Carlo simulation. A simulation is a fictitious representation of reality. A Monte Carlo method is a technique that can be used to solve a mathematical or statistical problem, and a Monte Carlo simulation uses repeated sampling to determine the properties of some phenomenon. Examples: simulation drawing one pseudo-random uniform variable from the interval 0, 1, can be used to simulate the tossing of a coin. If the value is less than or equal to 0.50, designate the outcome as heads. But if the value is greater than 0.50, designate the outcome as tails. This is a simulation, but not a Monte Carlo simulation. Monte Carlo method: pouring out a box of coins on a table, and then computing the ratio of coins that land heads versus tails is a Monte Carlo method of determining the behavior of repeated coin tosses, but it is not a simulation. Monte Carlo simulation: drawing a large number of pseudo-random uniform variables from the interval 0, 1, and assigning values less than or equal to 0.50 as heads and greater than 0.50 as tails, is a Monte Carlo simulation of the behavior of repeatedly tossing a coin. Kalos and Whitlock point out that such distinctions are not always easy to maintain. For example, the emission of radiation from atoms is a natural stochastic process. It can be simulated directly, or its average behavior can be described by stochastic equations that can themselves be solved using Monte Carlo methods. Indeed, the same computer code can be viewed simultaneously as a natural simulation or as a solution of the equations by natural sampling. Monte Carlo and random numbers: Monte Carlo simulation methods do not always require truly random numbers to be useful. While for some applications, such as primality testing, unpredictability is vital. Many of the most useful techniques use deterministic, pseudorandom sequences, making it easy to test and rerun simulations. The only quality usually necessary to make good simulations is for the pseudo-random sequence to appear random enough in a certain sense. What this means depends on the application, but typically they should pass a series of statistical tests. Testing that the numbers are uniformly distributed or follow another desired distribution when a large enough number of elements of the sequence are considered is one of the simplest, and most common ones. Weak correlations between successive samples is also often desirable necessary. Sawilewski lists the characteristics of a high-quality Monte Carlo simulation. The number generator has certain characteristics. The number generator produces values that pass tests for randomness. There are enough samples to ensure accurate results. The proper sampling technique is used. The algorithm used is valid for what is being modeled. It simulates the phenomenon in question. Pseudo-random number sampling algorithms are used to transform uniformly distributed pseudo-random numbers into numbers that are distributed according to a given probability distribution. Low discrepancy sequences are often used instead of random sampling from a space as they ensure even coverage and normally have a faster order of convergence than Monte Carlo simulations using random or pseudo-random sequences. Methods based on their use are called quasi-Monte Carlo methods. Monte Carlo simulation versus what-if scenarios. There are ways of using probabilities that are definitely not Monte Carlo simulations. For example, deterministic modeling using single-point estimates. Each uncertain variable within a model is assigned a best guess estimate. Scenarios for each input variable are chosen and the results recorded. By contrast, Monte Carlo simulations sample probability distribution for each variable to produce hundreds or thousands of possible outcomes. The results are analyzed to get probabilities of different outcomes occurring. For example, a comparison of a spreadsheet cost construction model run using traditional what-if scenarios, and then run again with Monte Carlo simulation and triangular probability distributions shows that the Monte Carlo analysis has a narrower range than the what-if analysis. This is because the what-if analysis gives equal weight to all scenarios, while Monte Carlo method hardly samples in the very low probability regions. The samples in such regions are called rare events. Applications: Monte Carlo methods are especially useful for simulating phenomena with significant uncertainty in inputs and systems with a large number of coupled degrees of freedom. Areas of application include physical sciences. Monte Carlo methods are very important in computational physics, physical chemistry, and related applied fields, and have diverse applications from complicated quantum chromodynamics calculations to designing heat shields and aerodynamic forms. In statistical physics, Monte Carlo molecular modeling is an alternative to computational molecular dynamics, and Monte Carlo methods are used to compute statistical field theories of simple particle and polymer systems. Quantum Monte Carlo methods solve the many-body problem for quantum systems. In experimental particle physics, Monte Carlo methods are used for designing detectors, understanding their behavior and comparing experimental data to theory. In astrophysics, they are used in such diverse manners as to model both the evolution of galaxies and the transmission of microwave radiation through a rough planetary surface. Monte Carlo methods are also used in the ensemble models that form the basis of modern weather forecasting. Engineering: Monte Carlo methods are widely used in engineering for sensitivity analysis and quantitative probabilistic analysis in process design. The need arises from the interactive, collinear and nonlinear behavior of typical process simulations. For example, in microelectronics engineering, Monte Carlo methods are applied to analyze correlated and uncorrelated variations in analog and digital integrated circuits. In geostatistics and geometallurgy, Monte Carlo methods underpin the design of mineral processing flowsheets and contribute to quantitative risk analysis. In wind energy yield analysis, the predicted energy output of a wind farm during its lifetime is calculated giving different levels of uncertainty. Impacts of pollution are simulated in diesel compared with petrol. In autonomous robotics, Monte Carlo localization can determine the position of a robot. It is often applied to stochastic filters such as the Kalman filter or particle filter that forms the heart of the SLAM algorithm. In telecommunications, when planning a wireless network, design must be proved to work for a wide variety of scenarios that depend mainly on the number of users, their locations and the services they want to use. Monte Carlo methods are typically used to generate these users and their states. The network performance is then evaluated and, if results are not satisfactory, the network design goes through an optimization process. In reliability engineering, one can use Monte Carlo simulation to generate mean time between failures and mean time to repair for components. Computational biology, Monte Carlo methods are used in computational biology, such for as Bayesian inference and phylogeny. Biological systems such as proteins, membranes, images of cancer, are being studied by means of computer simulations. The systems can be studied in the coarse-grained or ab initio frameworks depending on the desired accuracy. Computer simulations allow us to monitor the local environment of a particular molecule to see if some chemical reaction is happening, for instance. We can also conduct thought experiments when the physical experiments are not feasible, for instance breaking bonds, introducing impurities at specific sites, changing the local global structure, or introducing external fields. Computer graphics, path tracing, occasionally referred to as Monte Carlo ray tracing, renders a 3D scene by randomly tracing samples of possible light paths. Repeated sampling of any given pixel will eventually cause the average of the samples to converge on the correct solution of the rendering equation, making it one of the most physically accurate 3D graphics rendering methods in existence. Applied statistics. In applied statistics, Monte Carlo methods are generally used for two purposes: to compare competing statistics for small samples under realistic data conditions. Although type I error and power properties of statistics can be calculated for data drawn from classical theoretical distributions for asymptotic conditions, real data often do not have such distributions. To provide implementations of hypothesis tests that are more efficient than exact tests such as permutation tests while being more accurate than critical values for asymptotic distributions. Monte Carlo methods are also a compromise between approximate randomization and permutation tests. An approximate randomization test is based on a specified subset of all permutations. The Monte Carlo approach is based on a specified number of randomly drawn permutations. Artificial intelligence for games. Monte Carlo methods have been developed into a technique called Monte Carlo tree search that is useful for searching for the best move in a game. Possible moves are organized in a search tree and a large number of random simulations are used to estimate the long-term potential of each move. A black box simulator represents the opponent's moves. The Monte Carlo tree search method has 4 steps, starting at root node of the tree. Select optimal child nodes until a leaf node is reached. Expand the leaf node and choose one of its children. Play a simulated game starting with that node. Use the results of that simulated game to update the node and its ancestors. The net effect, over the course of many simulated games, is that the value of a node representing a move will go up or down, hopefully corresponding to whether or not that node represents a good move. Monte Carlo tree search has been used successfully to play games such as Go, Tantrix, Battleship, Havana, and Arima. Design and visuals. Monte Carlo methods are also efficient in solving coupled integral differential equations of radiation fields and energy transport, and thus these methods have been used in global illumination computations that produce photorealistic images of virtual 3D models, with applications in video games, architecture, design, computer-generated films, and cinematic special effects. Finance and business. Monte Carlo methods in finance are often used to evaluate investments in projects at a business unit or corporate level, or to evaluate financial derivatives. They can be used to model project schedules, where simulations aggregate estimates for worst case, best case, and most likely durations for each task to determine outcomes for the overall project. Use in mathematics. In general, Monte Carlo methods are used in mathematics to solve various problems by generating suitable random numbers and observing that fraction of the numbers that obeys some property or properties. The method is useful for obtaining numerical solutions to problems too complicated to solve analytically. The most common application of the Monte Carlo method is Monte Carlo integration. Integration. Deterministic numerical integration algorithms work well in a small number of dimensions, but encounter two problems when the functions have many variables. First, the number of function evaluations needed increases rapidly with the number of dimensions. For example, if 10 evaluations provide adequate accuracy in one dimension, then 10,100 points are needed for 100 dimensions, far too many to be computed. This is called the curse of dimensionality. Second, the boundary of a multidimensional region may be very complicated, so it may not be feasible to reduce the problem to a series of nested one-dimensional integrals. 100 dimensions is by no means unusual, since in many physical problems, a dimension is equivalent to a degree of freedom. Monte Carlo methods provide a way out of this exponential increase in computation time. As long as the function in question is reasonably well behaved, it can be estimated by randomly selecting points in 100-dimensional space, and taking some kind of average of the function values at these points. By the central limit theorem, this method displays convergence that is, quadrupling the number of sample points halves the error, regardless of the number of dimensions. A refinement of this method, known as importance sampling in statistics, involves sampling the points randomly, but more frequently where the integrand is large. To do this precisely, one would have to already know the integral, but one can approximate the integral by an integral of a similar function or use adaptive routines such as stratified sampling, recursive stratified sampling, adaptive umbrella sampling, or the Vegas algorithm. A similar approach, the quasi-Monte Carlo method, uses low discrepancy sequences. These sequences fill the area better and sample the most important points more frequently, so quasi-Monte Carlo methods can often converge on the integral more quickly. Another class of methods for sampling points in a volume is to simulate random walks over it. Such methods include the Metropolis-Hastings algorithm, Gibbs sampling, and the Wang and Landau algorithm. Simulation and optimization. Another powerful and very popular application for random numbers in numerical simulation is in numerical optimization. The problem is to minimize functions of some vector that often has a large number of dimensions. Many problems can be phrased in this way. For example, a computer chess program could be seen as trying to find the set of, say, 10 moves that produces the best evaluation function at the end. In the traveling salesman problem, the goal is to minimize distance traveled. There are also applications to engineering design, such as multidisciplinary design optimization. The traveling salesman problem is what is called a conventional optimization problem. That is, all the facts needed to determine the optimal path to follow are known with certainty, and the goal is to run through the possible travel choices to come up with the one with the lowest total distance. However, let's assume that instead of wanting to minimize the total distance traveled to visit each desired destination, we wanted to minimize the total time needed to reach each destination. This goes beyond conventional optimization since travel time is inherently uncertain. As a result, to determine our optimal path, we would want to use simulation optimization to first understand the range of potential times it could take to go from one point to another, and then optimize our travel decisions to identify the best path to follow, taking that uncertainty into account. Simulating industry problems using spreadsheet software is a powerful application of Monte Carlo simulation. With a basic spreadsheet tool and some formulas built into the sheet, industry can often attain good solutions without having to procure expensive simulation software. Inverse problems. Probabilistic formulation of inverse problems leads to the definition of a probability distribution in the model space. This probability distribution combines prior information with new information obtained by measuring some observable parameters. As, in the general case, the theory linking data with model parameters is nonlinear, the posterior probability in the model space may not be easy to describe. When analyzing an inverse problem, obtaining a maximum likelihood model is usually not sufficient, as we normally also wish to have information on the resolution power of the data. In the general case we may have a large number of model parameters, and an inspection of the marginal probability densities of interest may be impractical, or even useless. But it is possible to pseudo-randomly generate a large collection of models according to the posterior probability distribution and to analyze and display the models in such a way that information on the relative likelihoods of model properties is conveyed to the spectator. This can be accomplished by means of an efficient Monte Carlo method, even in cases where no explicit formula for the a priori distribution is available. The best-known important sampling method, the Metropolis algorithm, can be generalized, and this gives a method that allows analysis of inverse problems with complex a priori information and data with an arbitrary noise distribution. See also. Notes. References: Anderson, Herbert L. Metropolis, Monte Carlo and the Maniac. Los Alamos Science 14, 96 108 Bell, Stefan. A multiscale modeling of polymer materials using field-theoretic methodologies, a survey about recent developments. Journal of Mathematical Chemistry 46, 363 426 doi, 10.1007 per second 10910-008-9467-3 Berg, Bande Markov chain Monte Carlo simulations and their statistical analysis. Hackensack, New Jersey, World Scientific. ISBN A981-238-935-0. Binder, Kurt. The Monte Carlo Method in Condensed Matter Physics. New York, Springer. ISBN A0-387-54369-4. Kaflish, R.E. Monte Carlo and Quasi-Monte Carlo Methods. Acta Numerica 7. Cambridge University Press PPA 1 Davenport, J.H. Primality Testing Revisited. Preceding ISSAC 92 papers from the International Symposium on Symbolic and Algebraic Computation, 123A 129 doi, 10.1145/143242.1432990. ISBN A0-89791-489-9. Doucet, Arnaud. Freitas, Nandoda. Gordon, Neil. Sequential Monte Carlo Methods in Practice. New York, Springer. ISBN A0-387-95146-6. Eckhart, Roger. Stan Ulam, John von Neumann, and the Monte Carlo Method. Los Alamos Science, Special Issue, 131 137 Fishman, G.S. Monte Carlo, Concepts, Algorithms, and Applications. New York, Springer. ISBN A0-387-94527 C. for Astro and L. Zamora and D. Guirado and A. Lilina. A Monte Carlo tool to simulate breast cancer screening programs. Viz. In Med. And Bile 55, 5213. Bibcode, 2010 PMB, 55.5213F doi, 10.1088555021. Golden, Leslie M. The Effect of Surface Roughness on the Transmission of Microwave Radiation Through a Planetary Surface. Icarus 38, 451. Bibcode, 1979 ICA. 38451 doi, 10.1016/0019-1035, 79, 90199-4. Gould, Harvey. De Bochnik, Jan. An Introduction to Computer Simulation Methods, Part 2, Applications to Physical Systems. Reading, Addison Wesley. ISBN A0-201-16504-X. Grinstead, Charles. Snell, J. Laurie. Introduction to Probability. American Mathematical Society PPA 10 Hammersley, J. M. Hanscom, D.C. Monte Carlo Methods. London, Methuen. ISBN A0-416-52340-4. Hartman, A.K. Practical Guide to Computer Simulations. World Scientific. ISBN A978-981-283-415-7 Hubbard, Douglas. How to Measure Anything, Finding the Value of Intangibles in Business. John Wiley & Sons. PA 46 Hubbard, Douglas. The Failure of Risk Management, Why It's Broken and How to Fix It. John Wiley & Sons. Kahneman, D. Tversky, A Judgment Under Uncertainty, Heuristics and Biases. Cambridge University Press. Kalos, Malvin H. Whitlock, Paul A. Monte Carlo Methods. Wiley VCH. ISBN A978-3-527-40760-6. Croese, D.P. Tyem, T. Bottlov, Z.I. Handbook of Monte Carlo Methods. New York, John Wiley & Sons. PA 772. ISBN A0-470-17793-4. McGillivray, H.T. Dodd, R.J. Monte Carlo Simulations of Galaxy Systems. Astrophysics and Space Science 86. McKeown, P. Kevin. Stochastic Simulation in Physics. New York, Springer. ISBN A981-3083-26-3. Metropolis, N. The Beginning of the Monte Carlo Method. Los Alamos Science, 125 €130. Metropolis, Nicholas. Rosenbluth, Ariana W. Rosenbluth, Marshall N. Teller, Augusta H. Teller, Edward. Equation of State Calculations by Fast Computing Machines. Journal of Chemical Physics 21, 1087. Bibcode, 1953 JCHPH 21.1087 MDOI, 10.1063/1.1699114. Metropolis, N. Ulam, S. The Monte Carlo Method. Journal of the American Statistical Association 44, 335 €341 doi, 10.2307/2280232. JSTORA 2280232. PMIDA 18139350. M. Malik and J. Skolnick. Insertion of peptide chains into lipid membranes, an off-lattice Monte Carlo dynamics model. Proteins 15, 10 €25 doi, 10.1002/Pro 340150104. PMIDA 8451235. Mozegard, Klaus. Tarantola, Albert. Monte Carlo sampling of solutions to inverse problems. J. Geophys. Res 100, 12431 €12447. Bibcode, 1995 JGR. 100124331 MDOI, 10.1029/94JB03097. P. Ergida and M. Garcia and A. Londono and N. Y. Chen. Monte Carlo simulations of proteins in cages, influence of confinement on the stability of intermediate states. Biophys. Jure 96, 1076 €1082. Bibcode, 2009 BPJ, 96.107760 doi, 10.1529/Biofish 107.125369. Int Paynes L. De Nockerel, De Vliegewan, Torfsar. Trends and Uncertainty in Air Pollution Impacts and External Costs of Belgian Passenger Car Traffic International. Journal of Vehicle Design 27, 183 €194 doi, 10.1504/IJVD. 2001.001963. Int Paynes L, Rabler, De Nockerel, Torfsar. Diesel or Petroler? An environmental comparison hampered by uncertainty. In P. Sturm. Mitteilungen Institut für 1/4 of Verbrennungskraftmaschinen und Thermodynamik. Heft 81 Vol 1, 48 €54. Press, William H. Tucholsky, Soleil. Bettling, William T. Flannery, Brian P. 1986. Numerical Recipes in Fortran 77, The Art of Scientific Computing. Fortran Numerical Recipes 1. Cambridge University Press. ISBN A0-521-43064-X. Ripley, B.D. Stochastic Simulation. Wiley and Sons. Robert, C.P. Kaesler, G. Monte Carlo Statistical Methods. New York, Springer. ISBN A0-387-21239-6. Rubinstein, O.I. Croese, D.P. Simulation and the Monte Carlo Method. New York, John Wiley and Sons. ISBN A978-0-470-17793-8. Savides, Savakis C. Risk Analysis in Investment Appraisal. Project Appraisal Journal 9 doi, 10.2139/SSRN 265905. Sawileski, Shlomo S. Fraum, Gale C. Statistics via Monte Carlo Simulation with Fortran. Rochester Hills, Michigan, JMASM ISBN A0-9740236-0-4. Sawileski, Shlomo S. You Think You've Got Trivials? Journal of Modern Applied Statistical Methods 2, 218 225. Silver, David. Bennis, Joel. Monte Carlo Planning in Large POMDPs. In Lafferty, J. Williams, C.K.I. Shaw-Taylor, J. Zimmel, R.S. Culotta, A. Advances in Neural Information Processing Systems 23. Neural Information Processing Systems Foundation A. Serme Kalos, Laos ZLA Cubed. Monte Carlo Methods in Global Illumination, Photorealistic Rendering with Randomization. VDM Verlag Drive Mueller E. KISBN A978-3-8364-7919-6. Tarantola, Albert. Inverse Problem Theory. Philadelphia, Society for Industrial and Applied Mathematics. ISBN A0-89871-572-5. Vos, David. Risk Analysis, A Quantitative Guide. John Wiley and Sons. External links, Haswinkel, Michiel, ed., Monte Carlo Method, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Overview and reference list, MathWorld, Feynman-Cach Models and Particle Monte Carlo Algorithms, Introduction to Monte Carlo Methods, Computational Science Education Project, The Basics of Monte Carlo Simulations, University of Nebraska-Lincoln, Introduction to Monte Carlo Simulation, Wayne L. Winston, Monte Carlo Simulation for MATLAB and Simulink, Monte Carlo Methods. A Euro Overview and Concept, brighton-webs.co.uk. Monte Carlo Techniques Applied in Physics, Approximate and Double-Check Probability Problems Using Monte Carlo Method at orkic.net.